Hi everyone, welcome to this online presentation of our final project. In this video, we are going to talk about our analysis of data from 1961 to 1964 of the total coliform, also known as TC concentrations, at the northern, southern, and center stations along the coast of Huntington Beach. MATLAB was used to analyze the data provided for Group 2. We compared the CDFs, fit an analytical distribution that compared to each station, and found the best fit distribution for temperature and salinity CDFs and extreme value distributions.
Part 1, CDF comparison of log transform TC data. First of all, we combined all the north stations, all the data of the north stations and all the data of the south stations to make them into one big station for every respective one in order to make it easier for us to compare between one north, one south, and one center station. And when we plot the natural log of this, using MATLAB code plot CDF, we can see that the south station has the lowest probability of having a concentration of TC. Why is that? Because a CDF is finding a probability of X, a number, when it's less than a certain number. And in our case, we can see that, for example, the probability of natural log of TC at 0.0, which is the center, less than 4 is around 59%. As we can see from here, it's like 4, natural log of TC is 4 with the blue curve, and then it's like around 59%. This means that there is a 59% chance for the natural log of TC to be less than 4. When we compare this to the other stations, the north one, for example, we can see that natural log of TC at n less than 4 is around 61%, as we can see here from the graph. And the higher it is, the better it is, because generally, in a sense, like the higher the probability means that the higher the probability means that there is a less chance of having a higher concentration of TC in that certain area. Part 2, analytical distribution and mean hypothesis testing. Methodology of fitting an analytical distribution. We decided to use the log normal distribution equation to fit the analytical distribution. In order to do that, we chose 2 points for our empirical distribution, and using the natural log of TC and its probability, we were able to solve 2 equations to unknowns to find lambda and zeta for the north, south, and center stations using this equation. And then after finding lambda and zeta, we were able to plug it into the ERF function and plot it using MATLAB. And this is the example of the northern station. This is the southern station with the 2 points, lambda and zeta, and center station. This is the combined station fits. Based on just the first old graph, we can't just determine that the south one is the best for recreating. So in order to support our first assumption, we use this second graph in order to, which also says that the south station has the best CDF when considering the natural log of TC. And then we used another method of comparing the means. As we can see here, the mean of the north station of the normal values of TC is 634, mean of center would be 808, mean of south is 538. Since the mean of south is also the lowest, this furthermore supports our initial hypothesis. But just having a mean does not prove our point. We have to compare these means to make sure that they are if they are from the same population. What we did is, our first hypothesis is to compare the mean of the center station with the north station. And our null hypothesis was if they're equal, while our alternative hypothesis was if they're not equal. We did the same thing between center and south and north and south. Since there's an equal and does not equal sign, we use the two-sided test of the t-student distribution with type 1 error of 0.05, which has a 0.025 on each tail. And since our data points are 800 to 1,000, we use the degree of freedom of infinity since it's more than 90. When comparing every two means, we found the mean variance and the t-student statistic for each combination. The t-student statistic for center and north was 1.68, for center and south 2.7, and north and south was 1.38. Our threshold using the 0.025 on each side tells us that we can accept both north and south comparisons and center and north comparisons and reject the center and south comparison. Since t of center and north is 1.68, which is within the plus minus 1.96 tolerance, we can accept this. Since this is outside, we reject center and south, and then since this is 1.3, we also accept this null hypothesis. And then we can also see that we can see our means described in the graph. The south and north are close to each other, which is also shown here, north and south, by being close to each other and within the same population. And this is also true between north and center. But since south and center are further away from each other, they had different means, considerably different means, which made it seem like they are from different populations.
In part 3, our task was to take salinity and temperature readings and create CDFs for each. We were also required to test a variety of different probability distributions and compare them to the CDFs we created to see which distribution best fit each set of data. Using MATLAB, we prepared CDFs for temperature and salinity. As you can see right here, this is the temperature empirical CDF we found from the data, and this one was the salinity empirical CDF we found from our data. Also using MATLAB, we tested the normal, log normal, and beta distributions to see which one best fit the empirical CDF of the temperature and salinity. For temperature, as you can see from this graph here, our best fit seemed to be the log normal distribution, indicated by the red line in the graph. To provide statistical evidence for the best fit, we calculated the sum of square residuals, which is the SSR, the root mean squared error, which is the RMSE, and the R2 value. The best fit curve must have an SSR and RMSE values that are closest to 0. Meanwhile, the R2 is best when it's closest to 1. We can see from our values here that when compared to the normal distribution and the beta distribution, the log normal distribution had an SSR closest to 0, an RMSE closest to 0, and an R2 closest to 1. As for salinity, as we can see here by the graph, our best fit was the normal distribution. However, it was a very close margin when compared to the last. The SSR for this was 1.9924 and the RMSE was 0.0439. As you can see from the log normal distribution, this was really close to these. But from our analysis and the given parameters from before, we were able to see that the normal distribution best fit the salinity data.
Okay, part 4, proposed test, conditional probability of extremes. Since we had the option of choosing multiple different ways of doing this part, we chose to do the conditional probability of extremes. Well, we considered an extreme value. When finding extreme values, we considered what is around the top or bottom 10% to be an extreme value. Thus, we chose the TC data for greater than 1,000 are 7.6, 8.81, and all the way to 3.75% for TC stations, N15, N9, N6, 3, center 3, and all the way to S15, respectively. And we chose temperature greater than 19, which is 11.545% of the temperature data, and salinity less than 33.53, which is 12.36% of the data. We can see that all those data are around the 10% range. Estimating conditional probability. We first assume that the exceedances following the binomial distribution, as it will either be true or false, i.e. event occur or not occur. So the maximum likelihood estimate, MLE, for the probability that a given sample of TC greater than 1,000 threshold is p hat equals x over n, where 75, 87, 92, all the way to 37 are the x for the respective station over the total number 987. Also to note in this part, we in the beginning when sorting the data, we removed all the days that had missing points. We just removed the data of the entire day to make everything similar and coherent. Estimating conditional probability. These are the p hat that we got for every respective station. But in order to get the actual range of the probability, we found the variance of the maximum likelihood estimate for the probability of the binomial event. Using this variance, the actual probability is this plus minus the standard deviation, which can be seen in here. TC conditioned on temperature. For temperature, we tested probability of TC greater than 1,000 conditioned on temperature greater than 19. We then estimated the probability using conditional probability equation. P of TC greater than 1,000 conditioned on temperature greater than 19 equals P of TC greater than 1,000 intersected with temperature greater than 19 over a probability of temperature greater than 19. As a side note, for the p hat values of the conditional probabilities, check the MATLAB script. The results of the TC conditioned on temperature. As we can see in this graph, the probabilities are highest around 0.79, which is 7.9%, and lowest at around 1.5%. This means that the probability of TC greater than 1,000 conditioned on temperature greater than 19 is not that high, which means that if the temperature is greater than 19, that does not really make a change in the TC or incur a TC to have a greater value. Although there's like a weird combination, I don't think of the points. I don't think there's any relation to them. For the TC conditioned on salinity, we tested probability of TC greater than 1,000 conditioned on salinity less than 33.53. We then estimated the probability using the conditional probability equation, which is the same as the old one. And the same side note, if you want to see the exact probabilities, you can check the MATLAB scripts. The result of the TC conditioned on salinity. We can see that in this, there is an obvious linear increase and then a linear decrease in probability. And it ranges from around 1% to 28%. This is a high range, but since it's increasing towards the center and decreasing towards like the sides, this could mean that there are something happening in the Santa Ana River that affects the salinity, which incurs higher chance of having a higher TC value. Comparing two proportions. In order to test if our proportions are drawn from the same population, we use the following hypotheses and equation by formulating the z-score test statistic over the normal distribution. Our hypotheses were the null is P of A minus P of B equals 0, and the alternate is P of A minus P of B does not equal 0, where P of A is the probability of TC greater than 1000, and P of B is the probability of TC greater than 1000 conditioned on temperature or salinity. And to find the p hat, we use this equation. Since we are testing if it's equal or not, as we did before, we use the two-sided test with type 1 error of alpha equals 0.05, which is 0.025 on each tail. Comparing two TC proportions, are they really statistically different? From the normal distribution graph, we would reject the null hypothesis if its z-value is greater than ZC is greater than 1.96 or less than negative 1.96, as we can see from the graph. But our data, they were all within this range, which we can accept, and which means that we can accept the null hypothesis, or more, to put it more right, we can say that we reject the alternative hypothesis, which tell us that all the TC greater than 1000 and TC greater than 1000 conditioned on temperature greater than 19 are all drawn from the same population. We found the same thing in the conditioned on TC and salinity values, which are all the same except for salinity less than 33.53, and the data are, although they're a bit more spread out and closer to 1.96, they're all still within the acceptable range, which is the range of rejecting the hypothesis, the alternative hypothesis.